Video time start.
So basically, apart from that, some of my people who had asked, requested, some of them are there, my students, and few of my colleagues. I can see the names, so they are there. So that is should be fine, I think. Yeah.
Shall we start, sir? Okay. So good afternoon, one and all present here. Good afternoon, all the dignitaries present, students, teachers, and good afternoon to Professor Pal, who is with us today. Today is a truly monumental day. Nearly 100 years ago, the scientific minds, some of the best scientific minds came together, unraveling one of the living mysteries among us, the quantum world. So as we all know that, yeah, we will not be just discussing about a century of physics. We'll basically be looking with Professor Pal here. We'll be diving deep into the mysteries, the 100 years of quantum mysteries today. And obviously to introduce Professor Pal here, I would invite respected Principal Madam, Mrs. Vijayalakshmi Kumar ma'am, to kindly introduce sir and to the honors.
Thank you, Dr. Sarvashish Bhattacharya. It is my absolute honor and privilege to introduce Professor Shanti Pal, who does not need any introduction at all. Professor Pal is presently the Professor of Chemistry, Ashoka University, and former Director of Indian Institute of Science, Education and Research, precisely known as IISER, Kolkata, and CSI, National Chemical Laboratory, Pune. He was also a Professor of Chemistry at IIT Bombay and was a Professor at University of Arizona, Tucson, USA, University of Torun, Poland, and Institute for Molecular Sciences. He was instrumental in setting up electronic structure theory group at NCL. Currently, he is an honorary professor at IISER Kolkata and holds the position of Chair of the Chemical Division, Council of Bureau of Indian Standards. He is a distinguished theoretical chemist and has contributed to methodological and conceptual developments of couple cluster theory, to many body electronic structure theory, to the area of density-based chemical reactivity, as well as to catalytic and hydrogen storage materials using computational material science. He obtained his 5 years integrated master's degree in chemistry from Indian Institute of Technology, Kanpur in 1977, received PhD degree from Calcutta University, and was a postdoctoral fellow at the University of Florida, USA, and was Alexander von Humboldt Fellow at the University of Heidelberg, Germany in 1987. Professor Pal is Fellow of all 3 National Academics of Science, Shanti Swarup Bhatnagar Prize winner, and the inaugural Shastra CNR Rao awardee, and has several other awards recognitions. He was a founder member of the Executive Board of Commonwealth Chemistry and presently is board member of Asia Pacific Association of Theoretical and Computational Chemistry and in the Presidential Advisory Board of International Society of Theoretical Chemical Physics. He was the president of Chemical Research Society of India between 2014 to 17. He has published 320 papers. Yes, you heard it correct. 320 papers and has guided more than 45 PhD theses. This is a brief introduction of Professor Pal. I welcome all the students, the bright minds of their respective schools across the country who have joined together. GD Goenka Public School, Dakshineshwar, is pleased to welcome all of you, and over to Professor Pal without ado. Thank you so much. Sir, you are muted. You are muted, sir.
Yeah, thank you very much for your introduction. And I'm very glad to be invited by GD Goenka Public School, which is one of the top schools in the country. GD Goenka Public School is a big brand, and I'm very happy to be invited by the one in Dakshineshwar. Can I now first share my screen, right?
Sure, sir. Sure, sir. Over to you.
Yeah.
Over to you, sir.
Just a minute.
হ্যাঁ বলো হ্যাঁ বুঝে গেছি এখন ওয়েবিনারটা হচ্ছে না একটু পরে কথা বলছি হ্যাঁ 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 দুটো থেকে দিতে না হ্যাঁ 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 ওকে
Can you see the?
ইয়েস
Sir, we can see. We can see. We can see, sir.
Right. Okay.
Yes.
I'll just go to the full screen mode.
Yes, sir.
Yeah, thank you, Ms. Vijay Lakshmi Kumar, for inviting me to this wonderful webinar celebrating 100 years of quantum mechanics. We have titled this as 100 years of quantum mysteries, and this is basically a celebration of the fact that the quantum mechanics started 100 years back. Many of you, the children in particular, who are in class 11, 12, have heard of quantum mechanics, I'm sure, but it's a rather complex subject at your level. So I will try to demystify as much as possible. So welcome the children of the school and also other students who are PhD students and some of my colleagues, chemistry colleagues in different institutions across the country, whom I saw that they have also logged in. So I'm very happy to welcome all of them to this national webinar. Right now I'm in Ashoka University. Before I really come to the quantum mechanics, I want to tell the children that I will delve a little bit about your school, of course, but also Ashoka University, and little bit about the chemistry itself. Because I'm basically a chemist. So one of the things that I want to inform that quantum mechanics has been a subject of physics, many of you think. So what is a chemist doing? And I will try to tell that the quantum mechanics is a very intricate subject of chemistry. Unfortunately, that is not quite appreciated at the school level. Let me first go to the GD Goenka Public School. I'm very happy to be invited by the school because it's one of the top CBSE schools in the country. They look at education much beyond the classroom, and I think that is a very important theme in many universities which are actually practicing liberal education today. Academic knowledge, the values, skills, and resilience, continuous process of learning, and continuous learning is a very important part. And we have an inclusive community, and you are going on a journey of discovery. That is very important. It's a journey, so you don't end. And what is important is holistic growth on emotional, intellectual, and societal front. That holistic growth is very important. And of course, you have critical thinking. Everybody talks of critical thinking, but it's not very easy to have a critical thinking. As you'll see, one must have a sense of collaboration, empathy, and adaptability. Some of these, I believe, are the motto of GD Goenka Public School, because I have taken from Madam's own writing about GD Goenka Public School. And I think I just want to tell that how the university at Ashoka, which can be your landing place after class 12, immediately after 12, practices many of these things as I go along. So I just first want to use few slides as an outreach for the Ashoka University. But even before that, I should mention that another landing place for many of the science institutions are ICERs. Of course, today you have ICERs, IITs, central universities, NITs, and many state universities. So there are a lot of options for science. So I was in ICER Kolkata, one of the 7 ICERs, which actually inculcated research and innovation. In both innovation and research are two different things. Research derives knowledge. Innovation uses knowledge to give it back to the society. So this is Ashoka University. This is from one of the graduation ceremonies. And This is the free spirit that the Young Scholars Program show. This is a very important program of Ashoka University, where children at the school level come before they even get into Ashoka University or any other university. So I just want to tell you what is liberal education. The practice that we have, it is basically a freedom to choose what you study. So the children decide what they're going to study. So they can study natural sciences, social sciences, humanities, and all on the same goal. That is very important. A completely interdisciplinary approach. It has a breadth, as you can see. And of course, after years, when you go into major, you can get sufficient depth on a subject. Again, focus is on skills, just as in your school, critical thinking, problem solving, communication, and social awareness. But very important thing is that when you come in and get admitted to Ashoka, I must tell you, for all the children, you don't decide a subject. So this is not like a normal university where you do BSc chemistry or BSc physics. You just get admitted to a bachelor's course. And then you have to do what are called foundation courses. And eventually you decide your major. Within 2 or 3 semesters, you decide what would be your major and minor. So you have some credits for major, some credits for minor. And that is how you choose your subject. The subjects can be from natural science, one from social science, anything. So there is no intent. We have seen people who wanted to do economics major, after 3 semesters have changed to chemistry major, taking economics as minor. So you are never fixed to a particular subject. I think that is very important. So we are completely NEP compliant. We have a foundation courses, which are very, very important. In fact, many universities are now practicing foundation courses, which are very broad-based and not just science. So principle of science is one of the foundation courses, but we have 9 baskets. So we have foundation courses on mind and behavior, grade books, quantitative mathematics, thinking. So there are 9 such subjects and you have to take 1 in each basket. So there are 9 foundation courses. In addition, you do major and minor courses to the extent of total 160 credits. Each course typically is 4 credit. Unless it's a half course, then it's a 2 credit. So 80 credits are required for major, 24 credits are required for minor. And then you have a co-curricular activities. And those who are going to do major in science usually are encouraged to do another 12 credit of research under NEP. As you know, then you get degree BSc honors with research. BSc honors can be without research. You can also exit after 3 years with a simply BSc or BA degree. Whenever I'm saying BSc, it means either BSc or BA, depending on which is your subject or major, finally. But you don't have to decide when you get admitted. That is the beautiful thing about it. You look around, shop it, and then decide. I'm going to talk specifically of sciences, that we have these few subjects in which we offer major: biology, physics, chemistry, mathematics, and computer science. Each of these also offers minor. But there are interdisciplinary science majors, mostly with the computer science. A very interesting combination is computer science and entrepreneurship, which you will not get in many universities. Computer science and mathematics, computer science and philosophy. Let me first tell, why do you do science? You are a science student. So science you do because it provides a very basic expertise. You have a physics, chemistry, math, biology, geology, all of this together gives you a platform where you can do interdisciplinary research. Eventually, as a career, you can do academic research, just like we are doing. We are in academics, do research and teach. You can also go to industry, where you can do research with industrial relevance, and chemistry actually offers very good opportunities for doing that. Today, a lot of students are looking for alternative careers. For example, science communication has become a very, very important career. And I think you can go to national labs for doing research. So there are so many options that are open to you when you do science. So these are the opportunities that I have listed. Academic institutions, research laboratories, like I grew up in National Chemical Laboratory in Pune, which is a CSIR lab. Then there are Institute of Science, Indian Institute of Science, Bangalore, TIFR in Mumbai. Many of you have heard these names. ISCS right in the heart of Kolkata. Then you have atomic energy, space, defense, industry, as I told you. But a very important part that is coming up today is what is called entrepreneurship. That is the spirit of innovation in which you can start a company. If you have an idea is not sold to the industry, that idea is not accepted by the industry, you can do a startup. Government is giving a grant for doing this, and you can show that the idea works. So it's a very interesting opportunity that we can have. That's the opportunity for innovation. And of course, a lot of collaboration. There are a lot of background noise. I will request everybody to mute. Yeah. So today, collaboration is becoming a very important theme, and you will get an idea, you'll get an opportunity to do what is called international collaboration. I just want to tell you what is the difference between research that you know, like Newton's laws, relativity, quantum mechanics that I'm going to speak, and innovation. So research is called invention. Invention is another name of research. You might have already heard discovery. So that is also called discovery. So what it does, it actually takes resources from market or nature. What do you mean by market? Many of the faculties, children you may not know, they get grant from the government. Like now ANRF, previously Department of Science and Technology or Department of Biotechnology, they get grant, that's a market, or from industry. Or you can be inspired by nature to generate knowledge. That is called discovery, just like it happened to Isaac Newton. He was inspired by apple falling and he did the Newton's laws. All of you know this. But the innovation is a reverse process in which you transform this knowledge back to the market, contribute to the nature, contribute to the society. I hope it is clear. So the invention and innovation together forms a cycle. And very often in India, we stop at research. We do not do innovation. Because innovation, unfortunately, requires a more holistic ecosystem, which many institutions do not offer. IITs do, because they have a technology-centric places. Good IITs at least do. Good NITs also do, because they have also an ecosystem where they can do entrepreneurship. And many other engineering colleges do, but not necessarily science universities. And this is a very important part, because innovation not only requires risk-taking, but it also requires understanding of society, understanding of market, what the market demands are, and accordingly you try to create products. A very famous statement by Swami Vivekananda, many of you might have heard this: take risks. If you win, you will be the leader. If you lose, you will be a guide. This is actually a spirit of innovation, to take risks. Even if you lose, you will at least be a guide. In fact, I do not know if Swamiji knew the word entrepreneurship or innovation at that time, but he made this statement, which is today a very guiding principle of the innovation, so many years back. I must say, close to your Dakshineswar, where I was as an ICER director, I will not say much about it, but I took the initiative to get funding and start a company, Section 8 company, which is today called Rise Foundation ICER. And that is now breeding entrepreneurship. So it has got many potential startups. Today it has got more than 60 startup companies and doing very well in the place called Haringhat. Actually, when we started this, many people doubted whether ICER, Rise in ICER can do it. There are many other places. I know in Pune, when I was there, NCL Pune, I also used to head NCL Innovation Center, but that was Pune. And this was Haringhat, not even Kolkata. Kolkata things have failed, I must say that. But this is working, and I'm very happy to say this, that we have an incubation center at ICER. So those who will grow up and have an idea, you can approach Rise Foundation ICER. It's a separate company within ICER, and they will give you housing, they will give you a small space where you can try your experiment, lot of facilities. They will also hold your hands, how to write for grant, to get money. So it's a lot of interesting idea that you'll get. Unfortunately, Many people could not do innovation because of the statement by C.P. Snow that people are very proud that their science cannot be used practically. But this is not the way that one should look at science. In fact, one should look at what Louis Pasteur's philosophy is, that do science with an application. Coming back to just first chemistry before I go to quantum mechanics, chemistry is a study. I'll do it very quickly because you all know this. Chemistry is just a study of what matter is made of, how it behaves, how it changes. Think of it as learning the ingredients and recipes for everything around you: food, medicines, plastics, air, even your phone. Everywhere chemistry matters. It explains so many things, starting from cooking to plastics, metals, formation of rust, de-icing. It's a very important thing. Why they put salt to do de-ice. So understanding basic chemistry is extremely important. The key ideas in chemistry, and that is where quantum mechanics will come, and that's the reason I'm introducing this, is really atoms. They are the tiny building blocks of matter. From atoms, you go to molecules, and all of you know what is the difference between atom and molecule. Like H2O is a molecule, whereas a hydrogen, H is an atom. Then you can make mixture of different substances which can be separated. That's called mixture. You have a compound which cannot be separated. So I think very important thing. There's a chemical change, there's a physical change. Physical change is like ice melting to water. So I think these are very, very key ideas which are very important. Chemical change is a reaction. And then there are different states of matter. Chemistry discusses these physical changes between solid, liquid, gas, and now there is a plasma, acids, bases, just a key ideas. And of course, a very important part is a periodic table. I hope all of you have seen a periodic table. Periodic table is a very interesting chart which organizes all the elements by similar properties. It's a map. In a way, it's a map for chemistry. At the end, I can show something about periodic table if you have time. So these are the examples in daily life. All of you know this: cooking, cleaning, health, environment, 4 important areas. But there are almost every area that chemistry is important today. So like plastics that you are using and so on. What is important when you study chemistry? Focus on concepts, just like you study physics. The reason I'm saying is that in the school level, many people do not like chemistry. That is the reason I'm trying to tell this, because that is my experience. I took chemistry as a favorite subject, because when I got into IIT Kanpur, I could have actually taken engineering. All of you know IITs are breeding ground of engineering, but I decided to do 5-year integrated masters, which was given along with the engineering courses. And that too, I did not take MSc integrated in physics or maths. I went for chemistry because I knew chemistry is a subject which is a quintessential subject. From chemistry, you can go to any other subject, including law, medicine, forensic, industry of all kinds today. So it's a very important subject. But very important thing is that many people get lost in chemistry because they try to mug up. I do not know how it is in the school, what you feel, but chemistry has concepts just like in physics. Focus on these concepts before any memorization that you have to do. Some formulas you have to memorize, but that should be minimum. Use simple models and drawings. Excuse me, can you mute? Yeah, use simple models and drawings, and these are basically called ball and stick model to look at a molecule. Make flashcards for water, salt, acid, base. Watch short videos. They are very, very useful today. Internet, lot of sources are there. They will understand chemistry. Do short experiment. I think chemistry experiments are very, very important. Maybe not long, short one, because seeing is a very powerful way to understand. And I repeat this, to see what is happening is a very powerful way to then understand. But understanding is very, very important. So these are some of the quick glossaries of chemistry. All of you know this. But chemistry has a very important concept. They are built in thermodynamics, which you will read later, chemical kinetics, how fast the reaction takes place, and the perspective of quantum, which I'm going to now talk about. The quantum perspective is extremely important. many careers that chemistry will open up for you. Here, I'm not necessarily discussing just chemistry because it is a science subject, but it's an integrated within science subject, health, medicine, engineering, materials. But you can see each of these subjects is extremely interdisciplinary. Chemistry alone cannot do. Chemistry with biology, chemistry with physics, chemistry with engineering, like engineering chemistry is very, very important. Nutritionist. And of course, teaching and research is something that all of you can do. So I will just go to this final slide on chemistry. That remember, chemistry is a science subject after all. Just like you look at other science. Chemistry works on principles. There is no magic. The reason I'm showing you, many people show magic of chemistry. Just you add something to something, color changes, something happens, and you think, oh, how does it happen? It must be a magic. There is no magic. I want to tell the children there is no magic. Everything that happens works on a principle. And that is where concepts and physics, maths, everything come. So physics, mathematics, computer science, biology, chemistry are all integrated with chemistry. So it's a very, very important thing to realize. In fact, I get very upset when people show magic and call it a magic without explanation, because there is nothing called magic. Everything happens for a reason, and that reason is the science. So I think you should learn this. Don't try to mug up. This was one video. I'm not going to show it now. De-icing and anti-icing. You know that if you put ice, the melting point of water changes. The freezing point gets depressed of water, and that essentially means at a low temperature it can still remain. It can still become water. So that is very, very important. That it happens because of a very famous person called Raoult. It's called Raoult's law. You will realize this. Same way, if you cook at a high altitude, the boiling point depression, and if you can change with salt, if you put some salt, boiling point gets elevated. So that is actually used for cooking in the mountains. It's a very interesting idea that you will realize as a physical chemist. But let me tell you, modern chemistry derives a lot on a very important physics, which has been a mystery over the years, and that is called quantum mechanics. Many of our understandings of chemistry were ad hoc before quantum mechanics came in. Chemistry used to be mainly a synthesis subject, not quite knowing why it's happening, how it's happening. It was more of a magic. But chemists had somehow intuitively used to explain, even before quantum mechanics came. I'm not claiming that the quantum mechanics is the only way that chemists explain. People used to explain, but they were all ad hoc. There's a lot of ad hocism in this explanation, and that slowly is going out in the modern chemistry based on quantum mechanics. So quantum mechanics has started from mid-20s, I should say. It has been a game-changing science. It has introduced new paradigm, and I'm going to talk about that paradigm. Of course, it's an extremely disruptive thought. You will very quickly realize. The reason is that it has a probabilistic description instead of a classical certainty. In classical mechanics, and I just want to tell you in a very simple way, you know that a particle exists at this point. But when you come to quantum mechanics, which is applicable for very small particles, atoms and molecules, and unfortunately chemistry entirely belongs to that length scale, small particles. For all those particles, I cannot tell where the particle is. So for example, if somebody tells you this is where the electron is in a molecule, that's wrong. Because modern quantum mechanics says you can only say that there is a probability that the electron can be here. So you can have a map of probability, a mathematical function which will tell you the probability map, but you can't tell that the electron is here. And I'm going to come to Bohr's theory, which you all read. And I will tell you what is the problem with the Bohr's theory. So Bohr's theory has been Niels Bohr, whatever he did, he himself corrected by the advanced quantum mechanics. When quantum mechanics came, it was more of a theory. Nobody thought it could have a technology. But today, it has generated technology. So we call it quantum science and technology. There is a quantum technology. Very importantly, there is a quantum computing. In fact, just very recently, I've been talking about quantum computing, which is a very important subject. And of course, materials, which can be called quantum materials. They're usually two-dimensional materials which show a lot of quantum effects. Some of these are certainly advanced. You don't have to worry about it. But this is only to say that science has generated good amount of technology. I also want to have a challenging question. Could the discovery of quantum mechanics be predicted by a computer system from the existing rules in the 1920s? That is what AI does. If you look at artificial intelligence today, it scales whatever is known and tries to go to the unknown. Could AI have discovered quantum mechanics? My answer is no. My answer is no. Somebody may argue because there were no pre-existing rules to have said that particles do not have a position. Particles do not know where it is. And this was a bedrock of quantum mechanics. The mystery started from there because Heisenberg said there is an uncertainty principle. I hope all of you have heard the name of Werner Heisenberg. He's one of the fathers of quantum mechanics. And Heisenberg said that there is no certainty of a particle being anywhere. So it started with a lot of discoveries and the contribution of key physicists. But I must say there are three very important experiments which started quantum mechanics. One of them is called photoelectric effect. I believe in class 11 or 12, the photoelectric effect is today taught. It shows that the energy is only proportional to the frequency. If you do not have sufficient frequency of a wavelength, of a wave, electromagnetic radiation, however intense the light is, you cannot have electrons ejected. So the energy doesn't come from intensity. And that is what was known in classical mechanics, that the energy is proportional to intensity. But Einstein experiment showed that you need first certain cutoff frequency. So the energy depends on frequency. Then if you increase the frequency, the electrons which are ejected begin to have more and more kinetic energy. That is a very simple experiment. What happens at that point if you increase the intensity? Yes, something happens, but the energy does not change. More number of electrons get ejected. More number of electrons with the same energy. So the energy crucially depends on frequency. I think this is an experiment that I believe at this school level one should understand very well. So this actually started quantum mechanics, which got a Nobel Prize. Many people think Einstein got Nobel Prize because of relativity or something else, but Einstein got Nobel Prize for this experiment, photoelectric effect. And then it started the theory of quantum mechanics. And later I will tell you, Einstein is one of the disbelievers of quantum mechanics. He did not like quantum mechanics, but his experiment started quantum mechanics. The entire analysis was given by Heisenberg, Schrödinger, Niels Bohr, and so on. The second experiment is what is called black body radiation. Every black body is a perfect emitter or absorber of light. And classical mechanics showed that the intensity should fall in terms of wavelength. As wavelength increases, intensity should fall of the emission. However, the actual experiment is given here, where it first goes up and then goes down. That's a thick line. So the first part, which is the low wavelength region, is called the ultraviolet, could not be explained by classical mechanics. So that is why it is called the UV catastrophe. And again, Max Planck, with a very famous same relation that the energy is proportional to frequency, could explain the entire thing. Again, these are matter of details, but I just want to tell you this is one experiment which actually showed. So Planck did a lot of theory to show this. The third experiment, which was again slightly surprising, is the spectrum of the hydrogen atom, where they showed that the hydrogen atom emits radiation at a fixed wavelength, or rather not fixed, at a wavelength which changes discretely, but not continuously. If you look at why is it unusual? If you look at a cricket ball has a kinetic energy, has a potential energy. but I can change those energies continuously. Is it not? I can slowly increase the velocity. I can take the cricket ball up, down, and the potential energy will change continuously. But that's not the case for an energy of an electron in an atom. They have only certain energy levels which are discrete. Please try to understand, these are extremely game-changing ideas, all of these. And that is the reason quantum mechanics became mysterious and many people started disbelieving it initially. But the experiments are there. The reason I'm showing the experiment is that the quantum mechanics was not a pure imagination, but it came because of the experiments. Bohr, however, did a quantum mechanics much earlier, 1913, before the formal quantum mechanics came. What Bohr did was it's to say that there is a nucleus and there is an electron moving in orbits. Remember the word orbit. And of course, these orbits have different energy because Bohr used a very interesting idea that the angular momentum is quantized. I hope all of you know Bohr's theory is actually done well in the school. And from there, Bohr could say that the energies are quantized. So the energies are discrete, Bohr could find out. And Bohr said there is an emission, absorption between the different n levels, depending on lower and higher energy. And Bohr could actually explain. This, interestingly, almost right for the hydrogen atom. Now, why did we require a new quantum mechanics then? Bohr's theory is not full quantum mechanics. I'm again repeating. It's an early quantum model because there is an angular momentum quantization. So that's why it is called quantum model, but it is not fully quantum mechanics. What is wrong with Bohr's theory? Heisenberg said that I don't know where the electrons are. Look at Bohr's theory. It says that the electron is moving in n equal to 1 or n equal to 2 in an orbit, which means I know where the electron is. So this Heisenberg said is not quantum mechanics. Quantum mechanics, you cannot pinpoint electron. So Bohr's theory eventually was not right. Though, interestingly, Bohr got the hydrogen atom almost right. I'm saying almost because there is a fine structure, which I don't want to explain to you, electron nucleus interactions and so on, which is more quantum, but this is almost right. But as soon as you apply to helium atom or any other atom, Bohr's theory completely failed. So Niels Bohr acknowledged that his theory is not perfect. His theory can only explain hydrogen and what is called hydrogen-like atoms, which means atoms with a heavier nucleus but only one electron, like helium plus, lithium 2+, and so on. So then Niels Bohr actually joined Heisenberg, Schrödinger to develop quantum mechanics because Niels Bohr himself admitted. That is one of the good things that you can say about Niels Bohr. So it could not explain fine structure and so on. As I've written here, the limitations of the Bohr's model. Bohr tried to extend this model with an elliptical orbit, with Sommerfeld. It actually got into two different quantum numbers, n and l. It was better than Bohr's original model, but the orbits are elliptical, and a lot of things it could explain, even the relativistic corrections. I don't want to go into that, but even then it is wrong because you are still putting the electrons in an orbit. Electrons are not orbit, so when Bohr went to higher atoms, this still could not explain. Only the hydrogen was little bit more accurate. So what is the modern quantum mechanics? Where does it build on? One of the things that is built on is the second point that I have written. That is the uncertainty principle. That is, I do not know where the particle is. Now, this is a very fundamentally very difficult to accept. People keep on asking questions on that. I only have a probability. Bohr also said, not Bohr, the modern quantum mechanics, it is done by Bohr, that there is a duality between waves and particles. And this is a very, very difficult thing to understand. I'm going to come to that. That an electron is a wave, but it can be a particle at the same time. Wave has a wavelength, particle has a momentum. And quantum mechanics is completely done with the momentum and position. At least these are the two important variables. So it has a momentum and it has a wavelength. And Bohr actually related this with a very famous principle that is called that the wavelength is inversely proportional to the momentum. Higher the momentum, smaller the wavelength. And I'm going to come to that. That's a very important point where I'm going to go to the classical mechanics from here. So these are two very important points. And of course, the energy is discrete, as we already saw for the hydrogen atom. So these are three very important principles on which quantum mechanics is based on. And you can see each of them does not follow classical mechanics. So it's a complete mystery about how, so that is the reason quantum mechanics was a mystery. So what is a duality? Duality, de Broglie said that the wavelength is, sorry, this is a mistake. Wavelength is h over p. This is 1 over lambda, so please ignore this. So wavelength is Planck's constant divided by momentum. So I'm sorry about this mistake. But essentially, Bohr said that the wavelength and the momentum are inversely proportional. That is very important. To look at the wave particle duality, a very interesting experiment was done. That is called the double slit experiment. In fact, it's a very interesting experiment. It says that if you have a situation where both slits are open, the electron, which is described by a function, can pass through both the slits simultaneously and interfere. But in actual practice, if you do a measurement, it is either going through slit A or slit B. But what you see is a combination of these two. And this is the most difficult thing to understand, how this combination has come. Let me first show you this duality. Let me just try to, through another very interesting experiment, that was an imaginary experiment. It is called Schrodinger's cat. Schrodinger's cat experiment shows the following, that there is a cage in which there is a cat. Now, there is a radioactive element. The radioactive element, if it emits radiation, the cat will die. But the interesting thing is that that element itself is in a state where it can emit radiation or it may not emit radiation. And that is called the wave. That is what the wave function actually shows. That it has a wave function which is a combination of both the states. It may radiate, it may not radiate. There is a probability. So when you open the system cage, then you may find the cat alive if the radiation has not taken place. But there is only a probability. So somebody else does the same experiment at the same time, you may find the cat is dead because it has radiated. So this was a very difficult thing to understand what is happening. So whenever I am making a measurement, please remember the cat is either dead or alive. But outside, I do not know what the cat is. Only when I open and actually do a measurement, I will know whether the cat is dead or alive. This actually created huge furor. Because what is this? So Carlo Rovelli said a very interesting thing. What is real is actually what is real relative to us. We don't know what is reality. So this is where the mystery comes in quantum mechanics. It's an illusion. We don't know what is the reality. Because a quantum system can exist as a combination of multiple states, which is the wave. So superposition is a wave. As soon as I make a measurement, it becomes a particle. Another very interesting experiment by Wigner. Many of you may have heard Wigner. He's a very good physicist, and his friend Jimena. So they are doing an experiment in which there is a glass door in which Jimena is actually making a measurement on an atom. But to outsiders, this atom and the friend are in a superposed state. So what Wigner sees is a superposition. He doesn't know what will be the result of the measurement. But Jimena is already inside the lab and she has done the measurement. The measurement could be a spin, for example. There could be many measurements. So one of them is spin. So for Jimena, the wave function has collapsed to a particle. As soon as you have a measurement, it is called particle. So Jimena knows what is the spin, up or down, for example, and Wigner does not know. Wigner knows it can be either up or down, and they are within few meters. What is a reality? What Wigner thinks is a reality, or what Jimena sees is a reality? Instead of Jimena, somebody else goes. If Jimena finds it is an upspin, somebody else may find it's a downspin. Because originally the state was a superposition. So you can find either of them. This is a very interesting thing that actually was described in the Copenhagen talk. It is called Copenhagen interpretation of quantum mechanics. That only when you make a measurement, the wave function collapses. So the measurement, of course, gives you a number, but you cannot predict that number. And that is a very, very interesting thought in the quantum mechanics, which is a mystery which has happened. So it can be spin up and down, 2 electrons. Many people talk about today quantum information where there are 2 electrons, one is up, one is down. They go far apart, but as soon as you make one measurement, the other is automatically fixed because they were originally up and down. But I don't know which is up, which is down. All of you know alpha and beta, up spin and down spin. You have done that when you do Hund's rule, Pauli exclusion principle, etc. So quantum information, however far the second electron is, it is now pinned down by the measurement of the first electron. It's a very interesting thought. And this is how the quantum information is being passed. It does not depend on position and time. So a lot of interesting things are happening. And this has created a lot of problems. Let me also give you a sense of what is quantum. The quantum comes from a Latin word. Of course, these are the people who did Max Born, Heisenberg, Wolfgang Pauli. Quantum means it's a Latin word. It means how much. So in a way, it is called the lowest coin of money. So it can be 1 quantum, 2 quantum, 3 quantum, but not 1.5 quantum. If you have decided 1 rupee is your lowest coin of money, of course, today it is 10 rupees, let's say, then you have either 10 rupees or 20 rupees, right? You can't have 15 rupees unless you are doing GPay. GPay is a very different thing. That is classical mechanics, okay? And what we handle is quantum mechanics. I just tell in a joke. So in GPay, you can continuously change. But if you have cash, it is either 10 rupees or 20 rupees. You don't have a 5 rupee coin. So it is from the lowest coin of money that the quantum word has come. It's a Latin word. In fact, very interestingly, Heisenberg, as a history, I must tell you, 1927, he wrote a very interesting letter to his fellow physicist, Wolfgang Pauli, when he described the uncertainty principle. I mean, he wrote a paper already, but this principle was described for the first time. In the Solvay conference in Brussels, there was a lot of discussion, and Albert Einstein is one of the persons who did not like quantum mechanics. Interestingly, his experiment, don't forget, photoelectric effect started quantum mechanics, but he did not like, because he said, how can particle, you don't know where the particle is. You don't know where is the result of measurement. And he said there must be some hidden variables. Actually, you know, but you are not able to theorize because there are hidden variables. A very interesting work that the discussion that they had. One of the interesting books, if you want to read, those who are interested in philosophy, because it actually goes into philosophy, is by Hans Henning von Gutenberg and Alex Griffiths, Lively Journey Through the Early Days of Quantum Theory. Right in the 20s and 30s, great minds of physicists will fascinate you. In fact, very recently in this year, I entered a public debate. Many of you might have heard India Science Festival. So there is a public India Science Festival which took place in IISER Pune. All of you already heard about IISER. So Pune has one of the IISERs. In fact, because of my connection with National Chemical Laboratory Pune, I am also well connected with IISER Pune, though I was director in IISER Kolkata. So IISER Pune, I actually went on 10 January. I spoke in a debate. The topic of the debate is very interesting. The world is an illusion, a quantum perspective. And that's the illusion that I'm talking of. Wave or a particle. And even if it is a particle, what particle? If it's a superposition of 2 states, I can get either this state or this state. I can't predict. There is only a probability. It's a very interesting book. I can refer again those children who want to read. Putting the U in Quantum. It's available online, free, by Jack Savitsky. So those who want to take the photograph of this slide, you can take. Heisenberg in 1932, after winning the Nobel Prize in Physics, said very interesting statement. What we observe is not nature itself. but nature exposed to our method of questioning. So that's the illusion. We don't know what the nature is actually, but what we are seeing is a nature exposed to our method of questioning, which means our method of measurement. And who is measuring? So this is where the philosophy comes in. If Jimena measures, she gets an upspin. If I measure, I may get downspin for the same system, because it is actually a superposition of two states. With some probability, I will get this state or that state, but I can't predict who will get that state. So the observer becomes a very integral part of measurement. Now that brings in philosophy, what is called metaphysics. So that means measurement comes, outcome of a measurement comes because of an interaction between subject and object. Object is what you are measuring, subject is who is measuring. So it's a very interesting idea which led to huge amount of discussion of metaphysics. So those who are interested in metaphysics, philosophy of physics can actually go into it. And that is where the illusion, idea of illusion came. Not that the world, not that what you see does not exist, but you don't know in what form. So this was a public debate that I had gone into. I was speaking for the proposal, incidentally. I was speaking for the proposal, and there was somebody called Arun Kumar Pati, who is now in KIIT University, Bhubaneswar. He was speaking against the motion, but it became more like a panel discussion, because even Professor Pati was kind of agreeing to the quantum uncertainty, of course. But what happens as the system gets larger? This is the bigger mystery that I'm going to bring you before I end. What happens and what does the chemistry come in? Cricket ball, trust me, is also has electrons, right? All of you agree. Cricket ball also has electrons, atoms, molecules. However, I know where the cricket ball is. That's the classical mechanics. But at the same time, I'm saying that I don't know where the electrons are. I don't know where the atoms are. But a large number of atoms and electrons form the cricket ball. How do I know the cricket ball position? This has been a very big debate. What happens as the system gets larger? As system gets larger, we know now quantum mechanics, we can give up and apply classical mechanics. Large enough system, but how? So there are a lot of philosophical reasons. One of them is a very simple reason, that the uncertainty itself becomes smaller and smaller. Second reason is that the uncertainty, if you remember, Heisenberg said delta x, delta p was of the order of Planck's constant. The Planck's constant is a very, very small number. So the uncertainty is there, but it is so small that you are not able to measure now for the cricket ball, because cricket ball is very large. So the relative to the size, the uncertainty is smaller. So this is what Niels Bohr said, in the limit Planck's constant going to 0, all quantum principle will move over to the classical mechanics. It is a very interesting idea. H will never become 0. H is the Planck's constant. Remember, what Niels Bohr said is that in the scheme of things, H can be taken to be 0. I think you have to understand with a pinch of salt what it meant. So the uncertainty there, but it is no longer relevant. So at small scale, when it is atom, molecule, quantum mechanics is necessary. When it becomes large, you can do away with quantum mechanics. So the question is classical mechanics an approximation of quantum mechanics? This is a very, very provocative question, because all of you first study classical mechanics, then you will read quantum mechanics. And now I'm saying, maybe the Newtonian's law is an approximation to quantum mechanics. The real truth is quantum mechanics. In the large system, the approximation is Newtonian mechanics. Now, this is a very dangerous, provocative statement. You can go on debating this. So the how small is small, and that is where the chemistry comes in. You can see the smallness. I have given you angstrom and time, length and time. From angstrom to roughly nanometer, it is quantum mechanics. Then it becomes what is called today, I don't want to tell you, these theories are called molecular dynamics. A lot of people are working in MD, molecular dynamics simulation. There may be people who are listening to this. They are more classical. Then mesoscope is even more classical, and then you get engineering length scale. But the chemistry, atoms and molecules, is right here. biology is probably here. Biology is probably in MD and Meso. I'm not able to show it because of the online thing. So the biology is larger, like protein, membrane. You can do away with quantum mechanics. So many people who are working in biological system do not worry so much about quantum mechanics. Because first of all, if you want to apply, it's a very, very complex, cumbersome. But when quantum computing will come, you will see later quantum computers is a very potent thing, very, very fast computers. They might make even quantum mechanics possible to be applied for biological systems. So that's very, very important that the chemistry is in the quantum domain. And that is where I wanted to start, why I did chemistry. And I would like to finish with that note, that what we are going to do in chemistry is actually quantum mechanics. So all chemists must learn quantum mechanics. And this is where I end by saying that the world itself is not unreal. The mystery is that what we see is subjected to our method of examination. I want to go back to the Heisenberg's thing. What we may see is not the same as what everyone sees. So I hope you understand what is the mystery. With that, I think I will end here by saying, yeah, these are some of the these are things which are there for chemistry. It's not important for you, but let me just go to the end and thank GT Goenka Public School. Thank all of you for listening to this. What is the mystery in quantum? And I think that was the last slide which had the mystery in quantum. And of course, the principal of the GT Goenka Public School, Dakshina sir, for inviting me to give the talk. Thanks all of you. I've just taken about an hour. Yeah, not even an hour. I started 2:10, 2:15. So yeah, my time was almost an hour.
Wonderful, Professor Pal.
Thank you very much. Thank you very much. And I will like to have
And
questions.
as you know, our audience is full of inquisitive minds today. So
Thank you very much.
there
Yeah.
are some questions for you. Yes, so because of the time constraints, we had to handpick or select just a few of them for you to answer because of the time.
So should I come out of the slides?
Shomujit from Upashana Academy asks a very interesting question, sir. What is the relationship between quantum physics mechanics with consciousness? If I repeat the question, sir, what is the relationship between quantum physics mechanics with our consciousness?
Yes. So that is what I said, that there's a philosophy here. Should I unshare it? Will that help? So I can see the people actually. Hello.
So I think your presentation can stop now so that children can turn on the camera and we can see all of it.
I'm trying to stop the present. Is it already unshared? No, not yet. Because
We can see the presentation,
Yeah.
sir.
I still have the presentation. Yeah, okay. Let me unshare it now. Yeah, stop sharing. Yes. So yeah, it's unshared. Yeah. So this is a very important question: quantum mechanics and consciousness. I was actually telling you about the philosophy, metaphysics. So a lot of people relate it to consciousness. The consciousness is essentially, it differs from human to human. And this is where the Heisenberg uncertainty principle also said that depending on who observes, why does this thing come? Depending on the subject, your results change. So is that related to consciousness? On the other hand, the physics is physics. That is, we get a result. Although there is a probability of getting a result, that probability can be computed, which I did not tell you, is that probability can be computed once I know the function of a system. So physicists are happy with that probability. And from there, they at least can calculate what is an average outcome. So physicists do not want to discuss that it is a result of a consciousness. But indeed, you are right. If you are going into philosophy of physics, this is a very, very important question. And metaphysicists do discuss that quantum mechanics and the consciousness relationship. Yeah, so that's a very important question. So I think those who are interested can read some of the metaphysics text books.
Yes.
Okay.
Thank you, sir. Sir, next, Madhuja Sarkar from BDM International asks, imagine a future where quantum-powered AI Imagine a
Yes.
future where quantum powered AI becomes a reality. What are the
Yes.
three major benefits and what would be the three
Yeah.
possible risks for the
Absolutely.
society in that
See,
case?
just about a week back, I gave an interview on quantum computing, which was telecast in DD Bangla, Doordarshan Bangla, on 4th of July, just this Saturday, actually, last Saturday at 5:30 p.m. and repeated on Sunday. And I was asked the same question, that in the world of AI and ML, how quantum computing will impact. So quantum is impacting quantum computing because quantum computing is based on superposition of states. So these are called qubits. So those superposition of state means there are a lot of possibilities of doing computation. So the quantum computing can become very, very powerful. Because of that power, today I can generate a lot more data. So data is very important. Remember, AI works on the data. If you give a wrong data, AI will produce wrong results. So how quantum is going to impact? Quantum will immediately lead to quantum computing, and it is already going to quantum computing. That's one way that I can explain. Quantum computing will be so powerful that it can provide many, many data for large systems, which is not possible today. That data can enrich AI. So the AI will get more sophisticated because of quantum computing. And of course, AI is already trained to quantum mechanics. So that is not a problem. The probability, calculating the outcome, because it's not that we cannot calculate anything. Physicists calculate. What we calculate is an average value. Why? I'm again repeating. Although there is a probabilistic description, there is an illusion that probability can be computed. That is a mathematics that I did not show. Given the function, I know the probability. But I don't know who will get what. Just like if there is a toss coin in a head or tail, you know the overall probability is half for a large number of data. But you can't predict in the first test match whether India will call right or Australia will call right. Which test match who will call right? So that's the problem. So that is the observer. But overall, I know the probability. So overall, I can average out with a very large number of things. So physicists know this. So but today, this superposition is used for quantum computing, and that is going to impact the AI because it can now produce many data for large systems, and AI and ML will refine it. Machine learning will refine it, and I believe in years to come, AI can be much more reliable. Today, the reliability of AI is in question because we don't have that much of data. Yes, thank you.
Thank you, Professor Pal. The next question is from our host school, GD Goenka School, Dakshineshwar. Deeptaman Bhattacharya asks, how does quantum tunneling actually influence real chemical reactions? And what examples have most changed your understanding of its importance?
Yes, so actually quantum tunneling is a very important phenomena where you see that there is a potential barrier. The atom is not supposed to go there, right? That is the barrier, that's a tunneling. Yet, there is a probability that the atom could be on this side. So it means it has a negative kinetic energy. It almost looks like a negative kinetic energy, which is just not possible in classical mechanics, but in quantum mechanics is possible. So this quantum tunneling has led to many interesting effects of chemistry, which the chemists could not have understood. And this tunneling is a completely quantum phenomenon. Because of probability, one can actually show that even though potential is larger than the total energy, there is a possibility that the particle can exist there, which is impossible in classical mechanics because total energy is only sum of potential plus kinetic. Kinetic cannot be negative because it is square of momentum by 2m, right? But in quantum, that is possible. And that has generated new chemistry. So it has a really huge, for example, proton transfer, the small atoms like hydrogen, they have much more tunneling. I told you small is more quantum. Small is more quantum. So there's a hydrogen tunneling, which is very common thing in quantum mechanics. Yeah, so it has certainly impacted chemistry, understanding of chemistry.
Thank you, sir. So one more question. Farhan Ali from Spark School has a question. After 100 years of quantum mechanics, what do you think is the biggest unanswered mystery that scientists are trying to solve even today? the biggest unsolved ones?
Yeah, so this is a good question. One of the unsolved question, I will not say unsolved, but at least unanswered, is the application of quantum mechanics to large systems. Because even today, even though quantum mechanics is I can say it's the truth, I can't apply to very large system, to life cycle, for example, to industry processes. I can't apply quantum. But today people are doing. In fact, last year, Nobel Prize was given to a work in which it showed quantum effects even in macroscopic systems. So I think, according to me, in an unanswered, of course, there are a lot of unanswered questions, but I'm saying unanswered in this field is to look at, are there quantum effects which are very important in macroscopic systems, which are large systems, like in cricket ball? Are there quantum effects that we are missing? I'm saying yes, probably there are, we are missing, or there may not be. Newtonian law is perfectly okay to establish that. So that's a question that I cannot answer in this region. Quantum information. There's a lot to understand about quantum information, which is again unanswered. Quantum materials. People are looking at a lot of quantum materials, so people have some idea of a two-dimensional materials which are giving quantum, but not completely full idea of what quantum materials are. So this, I'm sure in another 50 years, people will answer many of the unanswered questions today in the realm of quantum mechanics. Once again, I restricted myself to quantum mechanics. Yes.
Now we would request the children to raise their hands in case they want to ask any question, and I would request everyone to turn on the camera so that we can kind of take a group photograph.
Yes.
Isn't it? So all the children are requested to turn on their cameras. And if anybody would like to ask a question, please raise your hand.
Yes, so I think Sohini. Somebody called Sohini has raised.
Sohini, so Sohini, please turn on your camera. And yes, your camera is. Please ask, put your question through.
Yes,
Good
Sohini.
afternoon, sir.
Yes.
Sir, my question is, sir, could you please elaborate the concept of multiverse?
Concept of?
Multiverse.
Multi-wall.
Multiverse, sir.
No, what is it? Multi-wall? I'm saying. No.
Multiverse.
Multiverse. She wants you to elaborate on the concept of the multiverse, sir.
Can you spell it?
Parallel universe, sir. Multiverse. The concept of parallel universes existing simultaneously at the same
I'm not able to hear actually properly.
Okay, ma'am.
Multi what? I mean, can you
So
spell it?
multiverse, VERSE.
Multiverse.
Yes.
Multiverse. Okay. So in what context? Multiverse has many contexts. In what context are you asking this question?
Sir, I wanted to ask merely in the context, like, is our life illusion? And you already answered that very beautifully.
Yes.
And in the context of quantum mechanics also.
Yes,
Like
so
what-
that is the multiple states that I was talking of. You are talking of multiverse in that sense, superposed states, right?
Yes, sir.
So, yes, of course, the world is superposed states in the small regime, but it is still not an illusion. I am again repeating, it exists, but it exists depending on the observer. So that is the multi. That is what I am seeing as an outcome is something else that you will see. And none of us is wrong. So there is no experimental error here. None of us is wrong. You are right, I am also right. None of us are wrong. So that because the original thing is a multiverse, what you are saying is a multiple state. So because of the multiple states, I can see any one of them. And this is an interpretation of that wave and particle. So wave is a collection of particles, if you see that way. Okay? As soon as I measure, it becomes one particle. But which one I can't predict. I can only tell the probability of which one you will get. And I talked about the Niels Bohr's principle. Lambda and momentum are inversely proportional. See, the mass becomes very large. Momentum is very high, right? If momentum is very high, what will happen? Wavelength will become very small. As soon as wavelength is very small, it almost becomes, so wavelength is very, very small. So it almost becomes single particle. It's always there. It's not moving much quickly, right? So that's an idea that for a large system, it is more of a particle. For small systems, it can be a wave as well as particle. It's a wave to start with. As soon as you measure, it's a particle. And that's a very important thing. Something can be a particle itself to begin with. And those are very complex things in mathematics. They are called eigenstates of an operator. So those are particles to begin with. There is no wave-like character, but otherwise there is a wave-like character which can become particle. So that is the multiwave. But if it is a large system, that multi will become more and more single. You have just one particle. Yes. Another question, Madhu, Debutra.
Please unmute yourself. Debotra Basu, yes.
Good afternoon, sir.
Yes.
Sir, I had one question. That what do you think that will have a greater impact on our new future? The introduction of quantum computers or the revolution of AI as our technology?
I think both will go hand to hand. Let me tell you, as I told you, quantum computer is going to enable AI further, strengthen AI, because it will generate data much more quickly. Right? Because quantum computer will be much more powerful. If it generates larger number of data, for larger systems, which I can't generate today, AI will be refined. AI will only become much more reliable. Today, AI depends on the data, right? If the data is wrong, AI is wrong. Prediction of AI is wrong. So there is no conflict. I would say quantum is going to only enable AI. Now, AI will work faster, provided you have a quantum computer earlier. Earlier, the quantum computer will come, AI will work even better. So they are really going to strengthen each other, according to me. Thank you.
Sir.
Then there is a question by...
Yes. Deeptaman. Please unmute yourself.
Ridhiman and somebody else.
Yeah,
Madhuja.
My question was, if
Yeah.
two particles become quantum entangled and are separated by thousands of kilometers, how can measuring one instantly
Yeah.
affect the other without anything traveling faster than light?
Yeah, so this is not really a space-time problem. So many people worry about that it is very far apart, but there is no space-time problem. So things are not traveling faster than light. That is a wrong thing. This is known because of an initial entanglement. Wherever it is, if it is an up and down, one of them is up, other is down. So it is simply that. But I did not know to begin with which is up, which is down. So once I make a measurement of the first particle, the second particle is fixed. So this is not that the information is spreading. No information is spreading because this is coming because of an initial entanglement at time t equal to 0. That is just been there. You can say in the consciousness of the two particles. If you want to now bring in philosophy, okay, in the consciousness of the particle that is there. So it will immediately tell one is up, other is down. Okay, so many people get confused with this quantum information. That is it going faster than light? No, there is no space-time sense here.
Okay, sir. Thank you.
Deeptaman.
Yeah, Madhuja.
Deeptaman Bhattacharya, please. Deeptaman Bhattacharya.
Deeptam
Then Madhuja.
and Shivam after that.
Madhuja Sarkar.
Yeah, Deeptaman, your question.
Good afternoon, sir. Quantum tunneling is a very relatively new term, not only to us, but actually the entire world. So,
Yes.
Recently, even a Nobel Prize was received regarding this, and it's a very new and very intriguing term, to be very honest. But so, what are the common misconceptions that students like us who are primarily
So quantum mechanics produce a lot of strange situations, as you can see already from uncertainty and all that. So this is a strange situation where the electron, if you look at classically, electron is in a state of negative kinetic energy, or the atom is gone to a negative kinetic. It's a strange situation. It's a strange only because you're interpreting it classically. So when you interpret it classically, it becomes very strange. That you are looking at a potential energy, kinetic energy, the way we compute, then sum it. These are all classical thoughts. So in quantum mechanics, suddenly this is not the way we will do it. So that is the reason you can see a probability, though the probability will be small and it will decay very fast. Even the tunnel stent decays very fast. That happens, but there is a finite probability that it can happen. And this comes directly as a result of quantum mechanics. So I would say this comes directly as a result of the probabilistic description of quantum mechanics. Very philosophical, but you will understand when you actually start calculating. It's a new thing. And very recently, the Nobel Prize has also shown that there is a tunneling effect in macroscopic system. Initially, people used to think only for atoms and molecules, but even in macroscopic system, the tunneling is there. Yeah, now, Madhush.
Yeah, Madhu Jal.
Good
Yeah,
afternoon,
Madhu.
sir.
Yes.
Sir, I had a question that it is said that time is not fundamental in quantum mechanics. Sir, could you please elaborate how
So,
is it clashing with the general relativity?
Yeah, so that is not quite true. The quantum mechanics that we are talking of, uncertainty is a position and momentum. Okay? But there is another uncertainty with the energy and time. That, yeah, so there is a fixed energy and fixed time is not possible. So that is how the time comes in, and the time comes in many other ways. For the position and momentum, when you talk of, the time is not an important thing, but there is an energy time in quantum mechanics as well.
Thank you, sir. Shrivam.
Shivam Ghosh.
Good afternoon, sir.
Yeah.
My question is that, do you think that due to the uncertainty and probabilistic nature of quantum mechanics, that it is revealing the human limit to understanding our nature?
You can say that. I mean, you can say that, but nature means at least small particles. If you are talking of small particle, I am telling you again, when the particles become large, these effects become unimportant. They may be there, but they're unimportant. But that is the reason the atoms and molecules became more difficult to understand. But as I said today, we can understand them because we know the probability of an event taking place. I'm again repeating. There is a probabilistic description. So if I know, and that probability today can be computed given the initial state of the system. That's the beautiful thing. And once I know the probability, I can calculate the average outcome. So everything is not bad. Everything is not crazy. So we actually give up. But if you do a microscopic measurement, a single measurement, then the uncertainty comes in. So, and indeed, this is a very difficult point when Heisenberg said, a lot of people, in fact, Einstein himself did not like it. Einstein was the biggest disbeliever of quantum mechanics. I hope all of you know. He said there must be a hidden variable, which you are not understanding, so you are packaging it in this manner. But nobody could disprove it. There are experiments in which they actually calculated the probability, they showed the average value over a long period of time or many number of systems. And the average matched. Absolutely. So that means their calculation of probability was right. Right? Then only the average could match. So I think there is a lot that went up behind. It has taken 100 years. Today we are talking of quantum mechanics as an established science. But in the 40s and 50s, people were disputing quantum mechanics. In fact, I remember when I was doing PhD in 1970s, late 70s and early 80s in the Indian Association for the Cultivation of Science, again in your city of Kolkata, I used to go to buses, public buses, like 8B or whatever. Those who know that area will remember 8B. And there used to be people who will come up, you know, with the Santiniketan style bag and pull out paper explaining to all of us who are sitting that the quantum mechanics is wrong. Will distribute that. You know, that was the spirit. I loved Calcutta city because of that reason. You know, the spirit is there that somebody in the bus can come and say quantum mechanics is wrong. Theory of relativity is also wrong, of course. You know, that's a different matter. But yeah, so many people did not. But today it has stopped. If you go to the bus, I have asked people, nobody says this. So it has taken time. Because a lot of experiments have taken. People have done experiments for cold atoms. In fact, all the qubits that we are talking of in quantum computing, they are basically cold atoms, which exhibit quantum effects very nicely, and many of them put together becomes a qubit. which is either a combination of not 0 or 1, but a combination of 0 and 1. That's again a superposed state. I don't know if it is 0 or 1. Normal computer works on bytes, 0 and 1. You may be knowing this is called qubits because it's a superposition of 0 and 1. So quantum computer actually works on the principle of superposition again. So this requires another discussion how quantum computer work. Yeah. So
we will take one or two more questions. The next one will be from Afrin and then Kazi, and then we will proceed for vote of thanks.
Thank you.
Good afternoon, sir.
Yes,
Sir, my question to you would be that, do you think what is the correlation between gravity and quantum mechanics? Like they either go hand in hand, or is there opposing nature
So
between
quantum mechanics shows there are a lot of violation of parity, and they are very thin, fine violation. In fact, I myself have been working on parity time violation. I have a lot of papers, but they come because of certain other subtle effects. They don't come automatically in quantum mechanics. They come because of what is called relativistic effects, which are basically interaction between electrons and nucleus. So they are very more subtle effects. So quantum mechanics can explain, but not necessarily the standard quantum mechanics. I was telling you that even for hydrogen atom, there is a fine structure, which is relativistic. So we have seen like lead fluoride, strontium fluoride. I have papers in Physical Review, Physical Chemistry journals, where PNT violation, so parity as well as time violation we have shown. Yeah, so it is an effect of quantum mechanics, but it's an effect of relativistic quantum mechanics. I'm again repeating, where the Hamiltonian, if I may say so, I have not introduced Hamiltonian in this lecture. Hamiltonian has to include electron-nuclear interactions, and not just electronic Hamiltonian. Normal molecules, we know how we do. That is a very important approximation by Max Born and Robert Oppenheimer. I think you have read, if you have seen the movie Oppenheimer, you will know. I don't know how many of you have seen the movie Oppenheimer. This is called Born-Oppenheimer approximation, in which the nuclei are thought to be fixed. The electrons have a probability around the nucleus. Probability, of course. But in actual case, it is not true. There is a subtle effect between electron and nucleus. They will give you this parity violation. Okay?
Yes, sir.
Yes,
Thank you, sir.
Yes. Kazi.
Good afternoon, sir.
Yeah.
So I recently came across an interesting question, which I think it is pretty interesting in quantum physics. Is our universe actually in a state of symmetry or in a state of super asymmetry?
So as I told you, there are very subtle effects which can break the symmetry. But these are very, very subtle. So in principle, you will see the symmetry in the universe, but they would be broken. And that explanation is much more subtle. It is not necessarily related to just having quantum mechanics, but having quantum mechanics with all other subtle effects included. So that is all I would say. But it's a more loaded question. The question is interesting. It's a much more loaded question. And probably if you are interested in physics, you will read more often. Yes.
Now we will vote of thanks group. Thank you so much, Professor Pal. Now we will move to the vote of thanks by our Honorable Vice Principal, Sir Dr. Aniruddha Bhattacharya, sir. Over to you, sir.
Thank you, sir. A very good afternoon to Professor Pal, sir, our principal ma'am. Thank you for giving me the opportunity to present the vote of thanks before you. First and foremost, I'd like to extend my deepest gratitude to our esteemed keynote speaker, Professor Saurabh Pal. Sir, thank you for taking the time out of your busy schedule and to lead us through 100 years of quantum mysteries. Sir, your pioneering insights into this quantum chemistry field and the scientific research have truly illuminated our minds and inspired, I think, everyone present here. Also, I want to express my heartfelt gratitude to our respected principal, ma'am. Thank you, ma'am, for your visionary leadership and constant encouragement. A special word of appreciation should be going to Mr. Sharbashish Bhattacharya, sir, our PGT, for anchoring and coordinating this entire session so beautifully. Thank you, sir. My sincere gratitude also goes to the principals of different schools across different states who made their students registered for this very, very interactive session. And I must mention the names of the schools whose principals actually felt that it is necessary to register their students. So we are thankful to the principal of Saidika School, the South Point Institute, Sharola Birla Gyanjyoti Guwahati, Saini International School Howrah, Shiny International School Maheshtala, the Stepping Stone School, Sri Santoshi Ma Academy, Principal of Upashana Academy, BDM International, Abhinav Bharti High School, Principal of Techno India Group of Public School, Garia, Barashat Indira Gandhi Memorial High School, Aditya Academy Secondary School, Barashat, Arambagh Vivekananda Academy, GD Goenka Public School, Purnia, GD Goenka Public School, Habra, Guru Nanak Public School, Techno India Public School, Navagram, and National High School. The principals of this school, my heartfelt gratitude goes to all of you for registering your students for this interactive session. Finally, a big thank you to our wonderful audience, all the fellow educators, students, and the science enthusiasts for your active participation and thought-provoking engagement in these very, very interactive sessions. Thank you so much once again. Thank you. Have a nice day ahead to all of you.
I have to say something of my
Yes,
thanks.
sir. Please, sir. Yes, sir.
So has the photograph been taken? I just wanted to know.
Yes, sir. Yes, sir.
It has been taken silently.
It has
Okay.
been taken. I'll share the photographs with
Okay,
you.
okay. Thank you. I must say that these are all class 12 students, right?
So 11 and 12 science.
11 and 12. Okay. But yeah, most of the students are very advanced, quite good. So I must thank all the students, congratulate them because they are studying very well. There are a lot of curiosity. So I'm very happy to say this. I have to thank the principal madam, specifically because it somehow happened that the background is something that I must tell. You can say a little bit accidentally, but she was connected to me by our ISER school, Garden High School principal, and she had listened to my webinar long back. I don't know when, 2021 or something.
So
Maybe.
I had hosted one. That was
Yeah, you had hosted. Yeah, right. You hosted one in 2021. So then suddenly after COVID and all that, of course, you always get disconnected. So I'm very happy that again we got connected and she immediately responded. I mean, that was a very good thing. So I have to thank her for her generosity and hosting me. And it was a pleasure to be here. And I have found her to be very, very fast in communicating. So everything, because it happened within a few days, actually, I must say. And so I have to thank her for bringing me here and thank, of course, all of you, the teachers, faculty who are here, and those who are present, who are not students, but present from outside. I must thank them. And of course, all the students. And the students are the backbone of this particular talk. And they have been wonderful. From the questions I can make out, they're very curious. And some of the answers are more complex than what they think. And some of the answers will not be known accurately, even many years from now. But the fact that they're thinking, I'm very happy. That thinking is very, very important. In fact, I remember somewhere some student asked, not in India, abroad, if atom had a heavy negative charge and a positive, light positive like electron, positron around, how would the world have changed? It's a very fantastic question. I just want to say that there are lots of interesting thoughts. Would the world, atom would have been still electrically neutral, but the negative core and positive outside, would the world have changed? But coming from a class 7 or class 8 student, I was fascinated. So I could see that whenever students ask questions like they asked, I'm very happy. So that is one of the reasons I must thank all your children. I think very good school I can see. And thank you, madam. Thank you, all of you. And I hope to see you again sometime, maybe in person sometime, or we'll see. Thank you. Thank you very much.
Thank you so much, sir. Thank you, children. Thank you, principals. Thank you so much.
Thank you.
End করো। We have a lot of things together, but we have done it.
এখনো লাইট করে
এই নাও, এতগুলো ছবি দিয়ে দিয়েছি। এই তিলক, এই ছবিগুলো আমাকে পাঠাবে।
নোট করা আছে।